called Best Flat Earth Video, Deniers Pull Their Hair Out with Both Hands, and it's by a guy named VHSJVC, who generally has some very good videos, and this one I think is particularly interesting because what he specifically addresses in this is stresses that are present at the end of spinning objects. And the reason that I bring this up is because there have been many times that Jaron has made the statement, as well as all of us, I think, where if we are spinning on a ball and with the equators running at 1,040 miles an hour around the outside edge, we are all in disbelief that it can't be felt. Of course, the rebuttal to that, most people will give the example of, well, if you're flying along in an airplane at 500 miles an hour, you wouldn't feel it, which is generally true. However, you are at an angle, so there's an angular momentum there that you would actually be turning at, and thus brings in centrifugal force, which can be a highly stressful force on any object. And in fact, one of the things that this particular video does is it makes a consultation to, what is it? It is the Machinery Handbook, I believe, is what he's actually quoting in here, the Machinist Handbook. And the Machinery Handbook basically talks about two different types of forces that are present on spinning objects. You have the angular velocity of the object, but then you also have what's called an edge velocity. And the Machinery Handbook goes on to state not only mathematically, but also gives the rule of thumb where it says that the general rule of thumb for engineering is the bigger the object, the slower the safe spin speed. Okay? You can have little ball bearing wheels. He actually gives an example of a ball bearing wheel in here that they're spinning up to, I don't know, how many, 80,000 RPM, something like this?
Yeah, something like that.
Yeah, here it is, 80,000 RPM. He actually does it right before this. Let me go beyond this. Okay, so here we have the digital tach, and it'll actually get up to about 82,000 RPM on this. Okay, so that's all fine because that's a very small object. But the next example he will give, and this is very interesting, of course it doesn't fly apart or anything like this, but it does get very close to 80,000 RPM. But the next thing he gives as an example is a jet engine. Now a jet engine, and this particular engine that he took, which was made by Rolls-Royce, he uses a demonstration that Rolls-Royce was using to make sure that should one of the turbofans actually break loose from the inside of the jet, that it doesn't actually pierce the engine housing or go into the cabin or anything like that, or start any fuel leaks or anything like that, because it could be obviously catastrophic. So what they actually do in this particular test is they put explosive bolts at the bottom of some of these fins that are spinning around. Now, the engine itself only spins at 3,000 RPM. However, they say that there's some ungodly amount of tonnage that would be represented at the ends of each of these fins, which are at the very edge of the 3,000 RPM spinning motor, okay? So that is the most dangerous thing. So one thing that had never really occurred to me when I was looking at this is that I didn't really realize that it was the edge velocity that was the most dangerous factor when you're calculating in stresses as an engineer. Of course, I'm not a mechanical engineer, but I have been definitely looking into this quite a bit, and it seems that that is absolutely the truth. So essentially, the reason that he chose this Rolls-Royce engine is because the blades, when calculated out, the velocity at the end of those blades at the diameter that they are spinning actually calculates out so that the end of the blades are running at about 1,000 miles per hour. And of course, as we all know, the equator of the Earth is allegedly spinning at 1,040 miles an hour. Now, the point that he makes here, and this is a very interesting point, is that because of the fact it is the edge velocity that is the most dangerous and destructive, and also contains the brunt of all the centrifugal forces, right? And here he's actually going to do this. He says, you might think that a bearing spinning at 80,000 RPM is going faster than a jet fan spinning at 3,000 RPM, and certainly both examples are going faster than a fake Earth spinning at 1 revolution per 24 hours, right? And the answer to that is wrong. The bearing spinning at 80,000 RPM does not come anywhere near 1,000 miles an hour. However, the Rolls-Royce jet engine does. So what he's doing is he's making a comparison of objects spinning centrifugally around in a circle and the stress forces that are present there. And what he's showing here is that when they actually cut loose that vane inside of the Rolls-Royce engine that's spinning at 3,000 RPM, the destructive force is absolutely unbelievable. There's so much energy there that it's almost like off the scale. And he's presenting that as an analog to the 1,000 mile an hour Earth spinning to demonstrate that not only would we absolutely feel that angular momentum, even though it only calculates at an angular velocity of 0.000694 RPM, the edge velocity of the Earth is 1,040 miles an hour. And if you think about the Earth and you just cut it into a whole bunch of little sections, what you basically have is a bunch of spinning gyroscopes with the one around the center of the Earth that has the fastest edge velocity. So, and again, he got all this information from the machinery's handbook, and he says that the stresses are related more to the edge velocity than anything else, and that is regardless of the radius of the object that's spinning. Okay? So velocity on the bearing going 280,000 RPM is only 250 miles an hour. The velocity of the turbojet fans is about 1,000 miles an hour. Okay? Velocity of the equator fake ball Earth is also about 1,000 miles an hour, 1,038, 1,040, whatever it is. You know, again, like I said, the rule of thumb is that the larger the object gets, the more stress it's going to have, the more angular stress it's going to have, okay? Edge velocity, because of the edge velocity being 1,040 miles an hour. So that's something that I had never considered, but the more I think about that, the more I absolutely believe that it's true, because he says here, disruptive force depends slowly on rim velocity. It has nothing to do with angular velocity, which depends on radius. And the more I looked into that, the more I have found that that is absolutely true. I actually had a brother-in-law that was a machinist, and we talked about spinning objects and things that he machined at a certain point, and he said you have to be very careful because you get things spinning at too high of an RPM and they literally will tend to disintegrate. And of course, like I said, the determining factor is that edge velocity stress. So when we take this and we scale up this effect all the way to the size of the Earth, you can imagine that not only would we feel it, not only would things be flying off into space, but it could be potentially very dangerous and destructive as well. And not only that, science would even kind of tend to go along with that, because when you think about it, science tells us that the reason that the ball Earth is actually an oblate spheroid is because of the centrifugal stresses that are present at the equator. They are so profound, in fact, that they cause the Earth to go from the perfect spherical shape that it would normally be like all the other objects in our solar system, right? But because it's spinning, the stresses are so great that it actually flattens the Earth out, expands out the equator due to these incredible edge velocity stresses, okay? So if it is strong enough, if the spin and edge velocity is spinning 1,040 miles an hour, which is strong enough to actually distort the entire shape of the Earth, then one would have to obviously think that how could you not feel that when you're out there at the equator or any point along it going beyond supersonic speeds. That's the thing that never really resonated with me. I understand that most people's argument is, well, yeah, it's one revolution per day, which, like I said, is 0.00694 RPM, okay, which in the large scheme of things, if you spin a frisbee that speed, it doesn't do anything. It's absolutely nothing. But when you scale it up to something the size of the Earth, it makes a huge difference. Now, here he is giving small demonstrations of people on a merry-go-round that are basically going maybe 20 miles an hour top speed, and people can't even stay on that. They're flying. They're absolutely flying off. And this is because of the edge velocity that's present on the merry-go-round. It has nothing to do with the RPM, but it's just the edge velocity. So if the edge velocity at 20 miles an hour is strong enough to throw these people off, we can only imagine what those forces must actually be at 1,040 miles an hour. Now, I am fully aware of both sides of the arguments. However, this is one particular area that I had never considered before. But to me, it makes perfect sense. And the more investigation I did of this little edge velocity fact that is brought forward by VHS JVC, the more I find out that it's absolutely true. And I don't see of any way that this can necessarily be debunked.